Next month on July 17th, so 1 month from today, it'll be a Friday. That is our annual picnic. Good food, fun time up there. We are asking for $20 just to help cover the cost. If for some reason that's not doable, but you still want to go, just talk to me, please. You know, we can work. We do have some sponsors that have donated some money to help us a little bit there. Other than that, I think everybody here is an SBE member. Not anymore? Hey, Dylan, you should join the SBE because there's some great educational opportunities.
Yeah.
And it helps the chapter out whenever you do. But other than that, I think that about covers it. Got a few more people coming in. Do I need to get some more chairs?
Oh,
I'll let
front here.
Cris take over here.
Will verify if the firefighters will be training or
I mean,
deal with that if it comes to.
they'll call me if they do. I have no say in it.
That's fine. Is it on?
Yeah.
All right. You folks ready? All right.
Ready to go.
A couple of months ago, the Alabama Broadcasters Association asked me to do a presentation on AM directional antennas. And so I'm going to give you an updated repeat of that. And it was pretty well received. Apparently they had a lot of people that, a lot of FM guys that had inherited AM facilities and they didn't really know what to do with them, So we tried to help them out just a little bit. So we'll talk about AM directional antennas today, care and feeding of AM directional antennas. This particular picture, by the way, this is one of our sites. This is WDCZ 970 in Buffalo. It's also Radio One has a diplex on. We own the site, but they diplex with us. That's why there's like 3 boxes at each tower base. That is Lake Erie in the background there. This site is right on the shore of Lake Erie there. So anyway, one of our sites. So who cares about AM anyway, right? Yeah, they're good. There's some folks there. It's still a viable media. We still transmit signals, and radios that have AM on them still work. You can tune them in and listen to our station. And a lot of AM stations, they remain, profitable. Our stations are profitable, most of our AMs, not necessarily all of them. Some of them are mission, we missionary efforts, I guess, but like here in Denver, 3 of the 4 are doing just fine. And AM stations since about 2017 or so have really become the gateway for an awful lot of FM translators. And those that are paired, if the AM is off the air, the FM can't be on the air either. Even if you had a transmitter breakdown or something, if the AM's off, you got to turn the FM off too. That's in the rules. But anyway, I think an awful lot of AM stations are still around just because of the FM translator. But guess what? You still got to maintain them. They still got to be in compliance. In a lot of ways, AM and FM are in the kind of the same boat. We've become just additional sources that are competing with all the other sources that are out there. We're competing in the automotive dashboard. FM is no longer king. I'm not sure what is king anymore. It's kind of hard to tell. But certainly, AM and FM together are kind of in the same boat. But as long as radio is the thing, AM will be around. And as long as it's around, we're obligated to, keep it maintained and legal. So why do you think AMs have all of those towers? Why do we need all those towers? Can't we just do one tower like they do with FMs? Um, the problem with AM is that it just goes a long way. and you know, it doesn't just hit the horizon and it's done like with VHF and UHF signals. It keeps going. You know, and it keeps going until it just fades out below the noise, and that could be a long way. And so we have to use directional antennas in a lot of cases to really have efficient use of spectrum, where we share spectrum with other stations that are on the same and adjacent channels. And so we use them to protect those spectrum neighbors. We use them to direct coverage into areas that we want to serve. We use it to direct coverage away from areas we don't want to serve. Examples of this would be coastal stations. You don't want to put a bunch of power out in the ocean. Nobody out there to hear it. So why waste all that energy? You know, so use a directional antenna to put the signal over the mainland. And it could be a combination of those objectives too. For instance, KLZ here in Denver on 560, one of our stations. It has a north-south airplane, I call it an airplane propeller pattern. And it's right up and down. It puts a strong signal right up and down the I-25 corridor. And it gets all the population centers, the major ones. And it doesn't waste any power to the east or any power to the west. The directional pattern of any AM station is defined by a mathematical formula, and what it does is it integrates the fields from all the towers to determine the signal level where you are. So if you're at an observation point P, you're getting signals from all the towers in the directional array. Each signal that arrives has an amplitude and a phase, and they vectorially add where you are to produce a signal level. And anyway, here's the formula. Everybody get that? It'll be on the test. So yeah, so it's a summation of, you know, just to break this down, it's a summation of the signals from all the towers at a given point. It's a three-dimensional exercise too. You know, we think of the directional pattern as being, you know, it goes in this direction, it doesn't go in that. You know, it has lobes and it has nulls. And that's true in the horizontal sense, but it also is true in the vertical sense. The vertical angle is really only of interest for night and critical hours because that's when the sky waves come into play. And if you start shooting it up into the sky, it's coming back down somewhere else, you know, and you've got to control that. So, you know, it is a three-dimensional thing. Well, that graph right there, that's of our 50 kilowatt KBRT in Los Angeles. That's the directional pattern. And right below it, well, I'm going to pass this around, let you guys look at it. This is a 3D, it's a, what do we call it? 3D printed, yeah. There's this guy that did the, he said he'd do a model of it for me, and I said, sure. So he did it. So you can see that it doesn't just have girth, it has height. And some places it has very little height, and some places it has a lot of height. And so you can see it's a three-dimensional exercise. And so, you know, if you've got a station that's out there in who knows where, you know, 1,000 miles away, and you've got to protect them at night, you have to limit the radiation at that vertical angle that will come down where they are. And so, you know, that's why you're looking at that one there. As it comes around, you'll see the nulls there, and some of those vertical nulls are very, very deep in that pattern. So, since monitoring a point in space is impractical, I guess, unless we just let a drone hover up there. What we do is we monitor a corresponding point on the ground, and that point has a mathematical relationship to the point in the air. And so we can tell, if this point goes high, then the point in the air is high too. And so we need to, so we know what we need to do there. So we can use this point on the ground as an indicator. What? Hope I couldn't see where I was. All right. So the FCC licenses, everybody's probably seen an AM license. They specify will that go away, Amanda? They specify a set of theoretical values. And if you have back up one, if you have did we miss a slide here? No, I guess we didn't. I guess I just missed a slide in my brain. So they give you a set of theoretical values, and we'll talk about those here in just a second. And they give you the theoretical values are what that formula would determine. If you plug those values into that formula, then it'll give you the horizontal pattern and the vertical pattern as well. But if you there's another set of parameters that's on your license. It's the operating parameters. Sometimes they're kind of close together. Sometimes they're completely different. And there's a lot of things that go into that. But the operating parameters, in other words, the parameters that you have to maintain on the antenna monitor to produce the correct pattern, they're determined during the setup and the proof of the array. And that can be quite the thing. We're going to talk about it here in just a minute. So they'll give you the tower number, they'll give you a current ratio, and they'll give you a phase for each of the towers. Conventionally proofed arrays, meaning a proof that's done with measurements in the field, will also have one or more monitor points. We hate monitor points, don't we, guys? Everybody nod. We hate monitor points. And it'll have a description and a maxima. And you can't let the field exceed that maxima. And we'll talk about that some more here in a few minutes too. But it's these operating parameters, including the monitor point, that the broadcast engineer is responsible for maintaining. A conventional proof is what we used for decades, really all the way up to about 2007. And what you had to do is you had to make the initial adjustment by making a bunch of field measurements along radial paths from the center of the array, and it was a lot. First, we start with a set of non-directional measurements using a single tower. It's usually the tower nearest the center of the array. We usually do it at 1 kilowatt, but sometimes it's at a lower power level. If 1 kilowatt would interfere with some spectrum neighbor, you might do it at a lower power. And then you measure from very close in out to 3 kilometers. And by very close in, I mean as close as you can get to the tower and still get an on-scale reading on the 10-volt scale, which is the highest scale on a FEM. And you start there, and that's and go out. Actually, you really reverse it. Today, in the GPS age, you could start near the tower and go out. In the old days, back when I was doing conventional proofs, we always started out because you could identify a point 3 kilometers out on the radio on a topo map. You could drive to that point, and then you'd walk into the tower, and because you could see the tower. And we would use a rope that had measurement marks on it to measure the distance as you go. And you take an awful lot of measurements on those close ends. I mean, like every 5 meters or so, you'd stop. So you wind up with this huge volume of points close in. And what that does is that takes all the conductivity out of the picture, and it tells you how much is being radiated along that radial path. We'll look at that here in just a minute. Then you measure from 3 kilometers out to 25 or 30 at greater intervals, 1 or 2 kilometers. So you make a fewer number of measurements, but at far field. And these non-directional measurements, including the far field ones, they're graphically analyzed to determine the inverse distance field along the radial. Why do we graphically analyze them? Because it's impossible to mathematically analyze them. This is a radial that this is one of the radials for KLVZ 810 here in Denver, the daytime array. We did this back in 2005. This was the whatever it says there, 340.5 degree radial. And anyway, you can see I made a whole bunch of measurements close in and then all the way out to whatever that is, 25 or 30 kilometers. And how did I wind up with an inverse distance of 212? Well, that's where the line fits. I literally plotted all those points and then moved the line until it fit the data. And you know, certainly as you get further out, the points are below the line because that's the ground conductivity coming into play. But up close there, see inside 1 kilometer or so, I mean, we're really nearly on the ground system at that point. And you can see that those points run right down the line. Those first few points there that kind of dip below the line, that's an interesting phenomena that you see. It's called proximity effect, and I think it's really kind of a standing wave that you see close in. And it's not uncommon to see a above or below dip or a bump close in to a tower like that. And do you ignore it? Yeah, pretty much. It's an error, and we know it is, so you kind of ignore it. So I analyzed that radial at 212, and I determined that from this graph. By the way, that other line there at the bottom, it says 15. That was a 15 millisiemens per meter conductivity line, and that was the best conductivity line that fit that data right there. And so you could say that we measured the conductivity out to that distance, and it's 15 millisiemens per meter. So at least on that one path, that's what it is. But that's pretty much what we measure around here is 15s and 30s. They're pretty high. If you get up in the mountains, you divide by 10. 1.5s and 3s up there. So then you got all these non-directional measurements, and then you put your array in the directional mode, and then you measure those points from 3 kilometers out again, and then you ratio those each one to the non-directional fields for each of those points, and then you take an average for the whole radial. You can either do an arithmetic average, you can do a logarithmic average. Whichever one you choose, you have to do for the whole pattern. You can't do arithmetic on one and logarithmic on the other. Logarithmic will give you a lower number. The arithmetic will give you a higher number. One of the requirements is that you have to meet 85% of the standard pattern root mean square for the array. So if you're having trouble in the main lobe meeting that 85%, you probably want to use the arithmetic average because it gives you a higher number. But if you're okay there, in good shape, but you're kind of bumping up against those null values, you can use the log average and get a lower number and get a little more breathing room. So they'll accept it either way. So then you take that average ratio and then you multiply it by that number, that 212 that I came up with, and that gives you the radial inverse distance field. And then once you've measured all the radials and you determine to be below the pattern maxima, then you pick one point on each of those null radials as a monitor point. And you know, there's a lot of things that go into that, but you better find a point that you can find. You better find one that's, you know, not going to be underneath a bunch of houses in a couple of years. And then the maximum field for that, the maximum that'll be on the license that you can't exceed, will be the maximum inverse distance field for that radial, that for the standard pattern, divided by the field for that whole radial that you measured, times whatever the field is at that monitor point. And that's what they'll put on your license. And here's an example. This here is the actual table that I submitted to the FCC for that radial. And so you can see there, all the distances, the point numbers, the non-directionals, the directionals, and that far right column you'll notice is the log ratio of each, and at the bottom is the log average, which is really it's kind of a misnomer. It's the anti-log of the log averages. Does that make sense? That's why if you look at that number and you go, wait a minute, that's a positive number, all those others are negative. Well, that's what happens when you average a bunch of logarithmic numbers that are, close to zero. And anyway, so we take that average and I multiply it by that 212, and then that gives me the directional IDF, in this case of 26.3, and the maximum IDF for that radial from the FCC was 31.6. So I was at what, 83.3% of the radial, which is a real good place to be. So we got about what, 17% of breathing room on that radial. So I've showed you one radial. You see all of these points. You see days and days of work. And how many radials? A bunch. So you get the idea. It's a lot of work. Obviously, there's some problems with this method. First of all, you've got to measure an entire radial to figure out what the maximum field should be at one adjustment point. So in other words, you measure that whole radial and you look at all the averages, and you've got to pick a point on that radial where the average is about what it is for the whole radial, and then you put a guy out there. It used to be we'd put him out there with a radio. Now you can put him out there with a cell phone and a meter, and you're doing this on all these radials, and then you're asking them, okay, give me a reading. You write them all down, and then okay, and I'm going to make a change on this phaser, changing a phase, changing a ratio. Okay, everybody read, write them down. Well, that went up, that went down, and it's like a monkey with the typewriter, trying to reproduce the King James Bible, it's kind of like that. It's a lot of trial and error until you figure out what the error vectors are and you get the thing adjusted. But really, it means you've got to measure each radial 3 times. You got to do the non-directionals all the way out. You do a initial directional to figure out your measurement point where you're going to put the guy with the radio or the cell phone. And then once you get it all adjusted, you got to measure it all again. So hundreds, could be thousands of measurements, and over days and days and days. Another problem is in all these arrays that are not in line with an odd number of towers, then the non-directional tower is not going to be in the center of the array. It's going to be offset from the center someplace, and so you've got this geometry offset from the very beginning, which doesn't really matter when you're 10, 15, 20 kilometers out, but when you're a lot closer in, it does matter, and so you have an error. A lot of things can influence the measured field at a given location. Stuff in the ground, stuff overhead, stuff nearby. So you can have a lot of errors in the measurement that you're doing. Nearby re-radiating objects can influence the local field without impacting the whole radial. And that's why we have to make so many measurements. Because the truth is, if you could trust one measurement, you could just do one measurement on each radial, call it good, and go home. But Doesn't work that way. So making field measurements and doing these conventional proofs takes a lot of time. It burns a lot of fuel and a lot of energy. And I don't just mean hydrocarbons, a lot of personal energy as well. These close-in measurements, the ones inside 3 kilometers, those got to be done on foot. And there's a lot of problems with that. Fences, a lot of them are barbed wire. Ponds, lakes, rivers, terrain features, angry pets, that was on my list, angry livestock, bulls, and angry property owners can, often make these measurements hazardous. And, I've done an awful lot of these, and a lot of them were done out in farm country. And, you really should go knock on the door and get permission to cross the land. But a lot of times you don't know who this land belongs to. Is it that guy or this guy? And do you really want to have to stop and go, walk half a mile to the farmhouse? And, it's easier to ask forgiveness and permission. So you just plow right on, But sometimes they would see you out there and come out and yell at you. And I've had them turn electric fences on me, things like that. So, it can make these measurements really, really hazardous. Here's a picture. This was at our Los Angeles area station in 2011. We set up it was a temporary antenna, and we got an STA from the FCC to put up a temporary antenna to do a conductivity measurement, a set of conductivity measurements at that site, because we didn't know what the conductivity was. And so we had to do the same thing for that non-directional antenna. We had to do a set of close-in, walk-in measurements to determine what the inverse distance field of the antenna was, so that we could, get it in the right place on the graph to determine where the conductivities were. And this is the kind of terrain we were dealing with there. That's Todd. You recognize Amanda. And really right behind where I'm standing was about a 50-foot cliff straight down. I think we got to that point, and I think we said, that's far enough. But you run into that kind of thing, and it's difficult. And I mean, if you see the direction they're heading and where we came from, all that, I call that scrub oak. They call it chaparral. It's chaparral. But we had to, work our way through that. And thankfully we weren't dragging a rope. This was in the GPS age, so we could actually just look at the screen and figure it out. And then this is the same site. You can see the towers in the background there. But, what if you need measurements in about 4 locations out there on that pond? I mean, I only know one guy that could have walked out there and got them. It wasn't me. So, that's the kind of things you run into. At KLTT here, we were proofing it as a new station, 670, 50 kilowatts back in 95. And one of the radios, and it was one of the monitored radios, I couldn't get around it, went right across Bar Lake. And it was December. And Jack Rowland was working for us. And Gary Bloodworth was working for us. And I have no idea where they found it, but they rented a little boat with a 10-horse motor on it. And they put it out there, and I went with them to the boat ramp. They launched it. On a cloudy December day, they were the only boat out there, I guarantee you. But we had a very early GPS, but it's all you could do, really. And so they went out to that 3-kilometer point and started motoring in with one of them was running the motor and calling off distances, and the other one was reading the meter and writing them down as they went. And they went until they hit the ice. And I told them, when you get to the ice, I'm just going to tell the FCC we couldn't go any further. There was ice. And I said, they'll just have to understand. Well, I stood there on the boat ramp. I was just watching them. And they crashed into the ice. They put it in reverse and they backed out. I thought, okay, good. And they swung around. And next thing you know, they run it up to full throttle and crash back into the ice again. No. And I'm watching them as they do this over and over and over again. And they worked a couple of 100 feet up into the ice there and got a couple of more measurements, and then the motor wouldn't start. Yeah. And they're pulling on it, and pulling on it. And I'm seeing all this activity in the boat, and they're half a mile from me. I mean, I was yelling, but they couldn't hear me. And I was just waiting on Jack to, you guys know Jack. I was waiting on him to get out of the boat and try to walk across that ice to get out of there. Thankfully, the motor started and he didn't. He didn't do that. But that was the kind of thing we had to deal with on these close-in, measurements. It can be a difficult thing. Well, let's talk about something more pleasant. Moment method proof. In 2007, the FCC began allowing licensees to make calibrated moment method models of their directional antennas and then use those to determine the parameters from those models. And it's that calibrated thing that legitimizes them. So what we do is we match the model to the real world. And here's how we do it. We make a set of base impedance measurements for the towers. What we do is we measure each one by itself with all the other towers either floated or shorted. It depends on the tower height. If your towers are shorter, like below 120 degrees, you would float the towers. They would just be open at the base. If they're above 120 or so, you'd short them. So you do that at each. You measure all those towers, the base impedance, and then you build a model. You actually build a series of models. You build one for each of the towers, but each model has all the towers in it. You're just driving one different, for each tower. You drive one tower in each model with all the others with an open at the base or a short at the base, depending on what you did in the field. So in other words, you create in the model the same conditions that you had when you were out there making the measurements. And then we calibrate that. We adjust our model so that those impedances match. But there's another small monkey wrench you got to throw into the works here. There's stuff in the base area of the tower that impacts those impedances. There is a base insulator. That's a capacitor. It has a fixed amount of capacitance. There is a series piece of feed tubing. I don't care if it has a coil in it or not. A straight piece of feed tubing will have inductance. If there's an isocoupler on the tower, that'll be another capacitor and shunt across the tower. Static drain choke, lighting choke, all of those things, and you have to take those into account. And so what we do is we build a nodal model. You can use SPICE, you can use any number of programs to build this model, and then you determine what the shift is in the impedance as a result of all of those things. And here I'll show you an example. This is one that this is that very one, I think, that we did there. You can look at the schematic there on the far left. That's a current source, and then there's a resistor in series. That resistor is not really there. It's a 1 ohm resistor in my model, and it's there for the sole purpose of creating a node at point 2 where we can measure the impedance. So you had to have a node there, and that's what that's for. That series coil there, that's the feed tubing to the tower. That first capacitor that you see to ground would be the base insulator. The other one is an isocoupler. And then that resistor represents the impedance of the tower, the modeled impedance of the tower. Now look at the very bottom there, if you can see that. The R value there, this is what we modeled, was 67.6 plus J 153. So that's what that resistor was set at. And we ran the model, and then we look at node number 2, there, and it's in red on the far right where it says 2 impedance, and you see that that 67.6 got transformed to 71.4. And you see the reactance, that 153 got transformed to 163.1. So you see there's a shift through that circuit of just the stuff in the base of the tower, and you have to account for that because you're not measuring on the base insulator, you're measuring at the output of the antenna tuning unit. You're measuring where your sample transformer is, because that's where the antenna monitor is going to look at it, and that's where we have to do everything. So we have to account for all of that. So we build this model, figure out what those shifts are, and then we adjust the model so that that 2 impedance number comes out at exactly what we measured. I say exactly, you have some leeway. It's plus or minus 2 ohms, plus or minus 4% for both resistance and reactance. So you just got to get it pretty close. And you do that for all the towers. It's really not that hard to land on. It's a little bit of work to set these up, but really once you set one of them up, you can plow through them in a hurry. So then we adjust the modeled height and the radius of each tower, which is a wire in the model, so that the model base impedance matches that other impedance there by within 2 ohms and 4%. So once we get that done for all the towers, then we run a matrix inversion program that gives us the sources that we need to feed the model to create the directional pattern. You know, so for each tower, you have to have a current and a phase, a source. You have to do that for each tower to create the correct pattern, and that's what that matrix inversion does. So then the model predicted base currents and phases, as modified by that circuit model that we showed you, are then determined as the array operating parameters. And there you go. Once you get to that point, you got what you need to make your pattern looking at the antenna monitor. Now, if you use sample loops instead of base transformers, there's a method that you have to use in the model to determine the elevation of the sample loop up on the tower. And you put the sample loops there, and then you actually look at the current at that elevation for each tower, and then you figure out the operating parameters that way. It's really almost easier with sample loops in terms of the model, but it's a whole lot harder in the field to hang sample loops up on a tower and isolate the sample line and all that stuff. So anyway, here's an example of this one. This is that same one. The peak current magnitude there in that column, that's from the model. That's for the lowest, the base segment of each tower, and then the phase, the same for the base segment of each tower. And then that next column, the current offset, that's the current shift through that nodal model that I showed you for the base. And then the phase offset is the phase offset through that. So you do get a little bit of current and phase offset, and you have to account for those. And then from that, we can derive the antenna. So those last 2 columns, there's your operating parameters right there that you use for to make the pattern. It really doesn't take all that long to do, to tell you the truth. This is a far more accurate method of determining array operating parameters, and it eliminates all those environmental factors that you don't have any control over. It requires no repetitive field measurements, no close-in measurements, no monitor points. And then there's what we call a clean site philosophy. And what this means is that it's clean leaving my site. Whatever happens to it after that is not my problem. And that's not absolutely true, but it's largely true. The FCC has rules in place that protect against people building anything they have authority over, like a tower or any antenna support structure close to your site that would affect your pattern, then they would have to do certain things like detune the structure to keep from interfering. But what if some city builds an elevated water storage tank, 300 feet away? You have no control over that. You can't do anything about it. If it's conventionally proofed and that screws up your monitor points, then you're on the hook for it. But if you go with the moment method, clean leaving my site, I can't help what happens to it after that. Amanda and I, we tuned up that site that I showed you the couple of pictures of the walk-ins on out there in Los Angeles. The towers, it's all brand new. The towers were up. Everything was done, and we went in there. I don't remember what day of the week it was, but she and I made the impedance measurements, and then we went to the hotel. She went and watched a movie someplace, and I went to work on the model. And before I went to bed that night, I had it all done. And so the next day, we went back out to the site, and really by that next afternoon, we had it all dialed in, had all the impedances matched for 1-to-1 SWR and all that, and we were essentially done. So in 2 days' time, really about a day and a half, we completely proofed that array and had it ready for operation. So that's the kind of thing you can do, with the moment method. I won't tell you about her turning the transmitter on while I had my arm inside a coil. It was my fault. I was turning it on, turn it off. I got my ons and off mixed up. She did what I told her to. It hurt. Turn it off, turn it off. Yeah. All right, so let's talk about directional array operation here briefly. You got to keep those parameters within the FCC values, and you guys know what the limits are. They're 5% for ratios, they're 3 degrees for phases, and if it's conventionally proofed, your monitor point must be below the maxima, whatever is listed on the license. Directional arrays do drift. Does that surprise you? Some worse than others. And there's all kinds of reasons for that. Ground conditions, wet to dry, frozen to thawed. They're prone to impact the self-impedance of the towers. And because they impact that self-impedance, they impact the current ratios and the phases. We see, it's like we get a little frost on the towers, right? We see a pretty good shift at some of our sites. That's the kind of thing you can, and she doesn't mess with it because she knows as soon as the sun comes out, it'll clear off and be gone, and it is. So components are prone to change value with temperature. Coils will expand with heat and contract with cold. Mica capacitors are the worst. They're especially prone to value changes with time. And I'm not talking about them, heating up and cooling down. There is some of that, but I'm talking about them shifting and staying shifted, or shifting and continuing to shift over time. It may be necessary, particularly with changing ground conditions, to make seasonal or even daily adjustments to the phaser to, keep the operating parameters within limits. And there's a lot of things that can influence the field at a monitor point. And most of those are, like I said earlier, beyond the broadcaster's control. A re-radiating objects like power line towers, elevated water storage tanks, cell towers, communication broadcast towers, multi-story tall buildings and structures. Cranes, it's a good point. Out at our 810 site, one of the impetus for us doing the moment method on that was that just south of our site there, right in the main lobe, right on the corner of Well County Road 4 and Highway 85, this crane company set up shop, and they have half a dozen big old cranes sticking up in the air all the time. Well, you can guess. And it's changing every day. You know, and there you could just guess the impact it had on our monitor points, you know, and there's just nothing we could do about it. You know, so yeah, cranes. You know, if the re-radiating structure has an ASR, antenna structure registration, or has an FCC licensed station of some sort on it, that licensee has the responsibility to detune that structure to protect your array at their expense. But even that turns into a fight, you know, especially if you're a tenant on that site and you don't own the tower and the tower doesn't have an antenna structure registration, you know, then who's responsible for it? It can be a real mess. And then for those non-FCC licensed structures, you know, you're on your own and you're probably going to have to bear the cost of the detuning. You know, once in a while I'll see, like I remember in Detroit, there was a 10 tower array there on the south side of Detroit. It belonged to Salem. I don't know if they still have it or not, but 10 towers, and it was in an ocean of big power line towers. Every power line towers had detuning skirts on it. And I guarantee you the power company didn't pay for that. That was that probably cost more than the broadcast station's array, detuning all those power line towers. And I just can't imagine maintaining all that, you know. By the way, this is kind of a neat thing here. I'll give you guys these. Amanda will publish a link to this, and so you can grab this. But if you want to measure the actual re-radiation from a structure you think may be re-radiating, it's kind of a cool procedure. You draw a line between the AM site and this potential re-radiator, and then you make the midpoint of that line a circle, or the midpoint of a circle, center of a circle, and then starting close to the re-radiator, you measure at points around the circle for about a quarter of the way around. And as you do it, you orient the FEM with, well, I say use the little electrostatic brake in the top of the antenna. Use it like a gun sight and point it right at the AM site. So that keeps your antenna perpendicular to the AM array, and it nulls the AM. And so you're only getting signal from the re-radiator. So you get all those points around the outside there, and then you plot them on a piece of log paper and analyze it just like I showed you. And you can determine that, wow, this monopole is re-radiating 200 millivolts per meter. That's a problem, you know. Or, oh, it's only about 2 millivolts per meter. That's not a problem. So that's how you can do it. Really a pretty cool procedure. I don't know who thought of it. I wish it was me, but pretty cool. So let's just say your monitor point does go high. What do you do? Well, you're supposed to reduce power to keep the monitor point below the limit, and probably get an STA from the FCC to cover you with parameters at variance while you're doing that. What you don't do is you don't go cranking on the phaser to try and fix it. You don't do that. A lot of times the re-radiation will be local, and by local I mean right there by that point, and it'll be something that's influencing the field at that one point, but it doesn't really influence the far field radiation. The only way you can figure that out is you have to kind of run a partial proof on that radial. So you measure all those far field points, ratio them, you know, do the analysis and see if it's below the standard pattern, and if it is, you're okay. I found most of the time that's the way it works out. You'll find it's whatever's causing you trouble is just affecting your monitor point, not the whole radial. But sometimes, you know, you build enough junk out there and it can affect the whole radial, in which case you got a real problem. But anyway, let's just say you do measure that radial, and now you see that, okay, my radial inverse distance is still good. So you can then file an application with the FCC to either get a new monitor point limit or to pick a different point. I would pick a different point, because if the pattern is disturbed this one now, it'll disturb it in some other way later, and you'll be chasing this thing for years to come. Anyway, it's still a lot of work, a lot of driving, a lot of gas, a lot of energy, a lot of paper. And moment method proof arrays don't have monitor points. I'm just saying, folks, you don't have to worry about that with moment method. Frozen ground, particularly in low conductivity areas, can have a much higher conductivity than thawed ground. We see that a little bit around here, but not too much. But in places that have low conductivity, it can be a 10-to-1 thing. I had a 50 kilowatt array on 1540 in Albany, New York. And man, every winter when the ground froze, the monitor points would all go way, way high. And, you know, I knew what it was. The ground had frozen. And of course, when the ground freezes, it expands and the molecules get more tightly packed together and they conduct. Conductivity goes up. So what did I do with it? I did a winter proof. I had to get the hire a guy to run a winter proof on it in the dead of winter when the ground was frozen. And then I got new monitor point limits that were okay in the winter, and they were real low, and my fields were way below the limits in the summer. But that's what we had to do. Wet ground conditions, particularly in otherwise low conductivity areas, they can have a higher conductivity than dry ground, and that causes high monitor point fields. Saturated ground. I know this is an alien concept to you guys that live here in Colorado like I do. We don't ever have saturated ground, right? But saturated ground, the conductivity will tend to go toward an 8, a value of 8. So if we're at 15 around here and it tends to go toward an 8, then it's no big deal. But if you're at 1 or 2 and it goes toward an 8, now your field strengths go way up and you can have a problem. So anyway, just something to recognize that you may need to run a proof when conditions are such that your fields are high, to get around that. Each directional antenna and directional pattern has a personality. I put that in quotes, meaning it behaves in a certain way. It drifts in a certain way with temperature and ground conditions. It responds to phasor controls in a certain way, and quite often it's not in accordance with the label that's on the control. It may say tower 1 phase, and you turn it and it's moving the phase a little, but it's moving the ratio a whole lot. Each control affects all the parameters to some degree, and the reason is it's a big closed circuit. Every control is in series with everything else is in series and parallel with everything else in the whole antenna system at the same time. And so anything you adjust affects everything to some degree. And it's how those parameters are affected that is part of this array's personality. And here's the thing, it's important for you guys that are maintaining these things to learn this personality and then use that knowledge in the array's maintenance and adjustment. So anyway, I won't hit those next 2 points, but they'll be in the paperwork. Just an example of how you can learn the array's personality and know that if I do this, I need to do this, this, and this at the same time, and now I can turn what would have been 4 steps into 1, and making a small adjustment. Okay, so what do we do when things go wrong? And they will. Step 1 is stop and think through the whole situation, all the symptoms, all the indications, and do some analysis of it. Put your thinking cap on. Do not try to fix an array problem with phasor controls. Your problem is not the adjustment of the phasor, unless somebody came in there and just cranked it. which happens, I guess. But you got to determine, is it a real problem or is it something with the sample system? And there's some things we can look at to determine that. First, look at the common point impedance. Look at the forward reflected power on the transmitter. See what those are. Then ask yourself, are the parameters of more than one tower affected, or is it just one? A real problem, in other words, a problem that really exists, that there's something wrong in the array, will usually affect the common point impedance, usually affect the forward and reflected power of the transmitter, and it'll show up in the parameters of more than one tower on the antenna monitor. So if the common point impedance is normal, usually 50 J0, and only one tower's parameters are impacted, then you need to be looking at the antenna monitor and the sample system, because I can almost guarantee you there's nothing wrong with the array. What you're seeing is a monitoring problem of some kind. You can swap the non-reference tower inputs to the monitor and then see if the problem followed the sample or stayed with the antenna monitor channel. By the way, the 1900 series monitors, Potomac monitors, they have an amplitude mode. You guys familiar with that? I think there's a test, normal, and amplitude. You put it in the amplitude mode, and it actually reads out to you the voltage, the RF voltage, RMS voltage of the incoming sample. And if you will, a good tool for you is to, when everything's working right, go through your towers and make a note of that as to what it is. And then if you have a problem like this, go back and look at that again. And let's just say all the amplitudes are dead on except this one. Well, that's right there, tells you your problem is in that one sample, or else all the amplitudes would be screwed up, right? So that's and of course, in the normal mode, you're reading a ratio. You're reading ratios of all the towers. And so they can be anywhere, if you have a problem, especially on the reference tower. But if you have those amplitude numbers written down, it's a really good thing to look at. Something else you can do is use a VNA if you have one to look at the sample lines. Does everybody in here have a VNA? Everybody needs one. And there's really no excuse not to have one anymore. And yes, we have some $20,000 VNAs. We have some really nice Agilent, a really nice Agilent one. We have a 2-channel, and we have a 4-channel Hewlett Packard that's the size of a city bus and weighs almost as much. We have all the tools and stuff to use those with. And they cost tens of thousands of dollars. And that's just to ship them around to various places. But then I bought this on Amazon for under $200. A lot of hams have these little nano VNAs, and they have SMA connectors on them. So I was thinking, man, it sure would be nice if they had one with N connectors. So I went on Amazon and I just put in nano VNA with N connectors. Bing, that picture came up. And in about a heartbeat, I ordered it. And so we took this thing out to KLZ, and I set up our real expensive Agilent, and I set this thing up, and we made a series of measurements. And let me tell you, this was fine. This was fine. I can't speak to what it, would do at UHF frequencies or whatever, but I can tell you at AM frequencies, it worked just fine. So anyway, I'll pass this around if you guys want to look at it. I'm going to pat everybody down on the way out, though, if it's okay. But seriously, Amazon, a couple of $100. There's really not much excuse to not have one of these things. Okay, so we want to look at a sample line. What do? This isn't really a sample line. This was just something I did for this presentation. When we built this place back in 2010, I ran an extra piece of RG8X up to the roof, just because I'm thinking, I'm a ham. I might want to do something up there one of these days. And so, we had a couple 100 feet of this stuff running up to the roof. And it's just in a box up there without a connector on it. It's open. And so I connected to it down at the in the TOC up there on the 12th floor. And I set this sweep up here from somewhere around 1 megahertz to somewhere around 3. And you'll see there's 2 zero crossings over there on the left side. And those zero crossings are resonant. Those are resonant frequencies. And the first one, the red one, is a 90-degree quarter wave. The other one is a 270 or 3/4. And so I was able to take those and get those frequencies. And then with that, I was able to determine the plus and minus 45-degree frequencies and get those impedances. That's the markers you see at the top and the bottom, plus or minus 45 degrees, which is 90 degrees on the Smith chart, of course. And then I was able to plug them into that formula right there. And I was able to see that my ZO, you see at the bottom left there, was 48.9 ohms. So I know the impedance of that sample line or that transmission line, piece of RG8X, was 48.9 ohms. That's probably pretty good for a piece of cheap, RG8X or whatever. But it also gave me the length of the line. And so you can do this with your sample lines too. And you can tell in a hurry, does this line have a problem or not? If it comes up at 50 or close to it, and then the length comes out what you think it ought to be, then, in about 10 minutes, you can do all of this and figure out that sample line's okay or it has a problem. And then you can do the same thing with it terminated into the sample transformer. But let me warn you about something. That sample transformer, out at the tower, you need to pull that output J plug, because otherwise there can be a lot of voltage coming in on that tower from other radio stations, even if they're 10 miles away. But a big piece of steel picks up a lot of voltage, and it'll be flowing through the ground, through the ATU components. And guess what? A big sample of that's going to be coming right back at your little analyzer there, through that sample line. And one thing you got to be careful about with these, really with all of these, even the big expensive ones, is they generally have about a plus 10 dBm input limit. And if you exceed that, then it can get real Western. and you won't like what it costs. So anyway, something to pay attention to. So just pull that J plug. But if you measure that terminated impedance, it should be right around 50 ohms. And I'll tell you why. It's because that sample transformer, I'm talking about the Delta, the gray Delta transformers, they have a 50 ohm non-inductive resistor that they're terminated with. And so that's what you should see when you, if you sweep them like that. So anyway, that's something you can do to look at your sample system. If you don't have a VNA, use an ohm meter. TCTs or sample transformers, they should show a pretty low resistance, because remember, they're just a coil. They're a transformer secondary, essentially. So you'll see that coil is a DC short, and it has a parallel, that 50 ohm resistor across it, which is, which won't even show up. So you should see that low resistance plus whatever the ohmic resistance of your sample line is, somewhere between 1 and 5 ohms, depending on the length of it and the kind of line you got. Sample loops should show a short plus the ohmic resistance of the sample line and the isocoil. And then you can disconnect the TCT or the loop and then check across your line, and it should show an open. So those are some things that you can do. Now that, I've had sample lines get wet before. They're buried. They get a little hole in the jacket or something. A prairie dog gets them, and you get a little bit of them that has a saturated dielectric, soaks up water like a sponge, and that may not show up looking at it with a DC ohm meter. I don't know. I never really looked at one like that with an ohm meter. That would show up for sure in the ZO if you did the VNA measurement. So something to think about. Then you isolate the issue to one pattern or the other. You have this problem on both patterns, day and night. If it's in both patterns, look at something that's in common to both patterns. An awful lot of these things have a different network for day, a different network for night at each tower, you know. And so if it's in both patterns, then that tells you that, well, it might be one of the towers that's common, you know, to both. Then visually inspect the phaser, look at the ATU components, look for swelling, look for cracks, look for seepage and other issues in mica capacitors. That's the most common cause of catastrophic directional array problems. This was our 50 kilowatt 770 station in the Bay Area last month. Yeah, I think I see the problem. Yeah, that was a mica capacitor that gave it up, and that's real typical for what you'll see with those. They're a potted. I don't know. They just, man, when they go, they just make a mess, and it's usually pretty obvious. Look for discoloration in coils, especially where the coil clips attach, the shorting clips. Rock those things back and forth. They should be tight. If they're real easy to move, you need to pull those things out of there and squeeze them together and put them back on. Check all the hardware for tightness, and I'm talking about where straps and tubing connect. You know, it should be tight. If multiple patterns are affected, look at the tower base areas. Look for foreign objects in the base insulator and so forth. A few months ago, Amanda had a problem at KLZ. It would not work right in the directional mode. And I think we're real low power. And so we went out there to the site, and she put it on the west tower non-directional, and it worked okay. She put it on the east tower non-directional, and it wouldn't run at all. So we knew right where to go. We went out there to the east tower, and it was obvious. There was a piece of braid that's used to ground the primary of the Austin ring transformer to the copper strap, and I guess it had broken off, and the wind had got it, and it flipped up and looped over the feed tubing to the tower and shorted out the tower. So I found a stick or something and and knocked it off of there, and boom, it all came back to normal, you know. So that's the kind of catastrophic thing you can find that sometimes is real easy to fix. Look up the tower and watch for broken guy insulators and evidence of carbon tracks, corona, and so forth. And if you got a drone, run it up there and look at stuff. What you see here at the bottom, these are three 24-inch fiberglass rod insulators. This came from that KBRT site in Los Angeles. This was about 3 months after we put it on the air. And one morning, they powered it up, and it said, nope. So I got on a plane and went out there, and didn't take long to figure it out. We got a tower crew to go up. I made base impedance measurements on the towers, and this one tower was way low. And I got a tower crew to go up. It didn't take him long to find this. We'd had some corona, and you know, as the corona would touch that fiberglass, it would burn it a little bit and create a carbon track, and that would grow and grow and grow over time until it essentially spanned the whole length of the insulator. And now, instead of an insulator, we had a resistor that current was flowing through. And you can see that top one there, it just delaminated completely. And that caused the short. You can see on those others some small tracks that were starting. And so I doubled those up on on that tower. That was the high power tower, had about 30 kilowatts in it. So I doubled those up. So we had 4 foot of insulators, and I put a corona ring on every single one of them right at the clevis where it attached to the tower. And it's been running ever since. That was in 2014, and we haven't had any issues with it since. But you know, that's the kind of thing, you know, that can happen, and you got to look for it. Check the temperature of your phaser and ATU components. Run the array at whatever power you can get it to run at for a few minutes. Shut it off. Use an IR thermometer and look and see if you see something hot. If you don't have an IR thermometer, again, you ought to have one. They're cheap, Amazon. But if you don't, you can just use the back of your hand and touch the various components. Warm is okay, hot is not. Hot means it's dissipating power, and it shouldn't be. Power should be going up the tower, not, heating up components. So a hot component needs to be replaced. And investigate the cause and fix it. Could be a loose connection. We're almost done, folks. Then check the transmission lines with a VNA or a bridge. And you can do the same thing that I showed you a minute ago, where you disconnect both ends, measure the characteristic impedance, and see if you got a problem or not. So then identify and fix whatever issue you find, and then, and only then, touch up the phaser controls. And you're not going to be making big adjustments. They're going to be small adjustments. So a few tips and tricks, just in the normal everyday operation. Watch for these seasonal variations. And especially be sensitive to ones that, like, you go from summer to winter and you notice you have to adjust this stuff, and now we're back in summer, but it didn't go back. That's kind of an indication of something that shifted, and you probably should pay attention to that. Could be a failing component, something that's changing value. And then another trick that a guy taught me years ago is that with everything working and the array adjusted properly for license parameters, shut the station off, and either with a VNA or a bridge, measure and record the static impedances of each branch of the circuit. So by that, I mean, I would measure at the output of each branch of the power divider, and I would write it down in there, and then measure at each transmission line output of the phaser, measure at the input of each ATU. And then when a problem happens and you can't find it, go back and repeat those measurements, and when you do, you'll find the one with the biggest change from what you measured back when is going to be where your problem is. It's going to be in that branch. So now you can really focus on where it is. ATU components live in a hostile environment, and you got to keep them clean, folks. Got to keep them free of insects, rodents, snakes, and their droppings, not just snakes droppings, but the rodent droppings, everything. Coil clips, particularly on ribbon coils, they can develop a series resistance or an intermittent connection. And this is particularly true in low power stuff. We have this problem on the 810 nighttime array, which is 430 watts. And it's just a constant battle that those ribbon cable clips just develop a little resistance. Sometimes the higher power stuff, it'll actually weld itself, and make its own permanent connection. But the lower power stuff, you get some corrosion on there, some oxidation, and it develops a poor connection. So regularly check those things, rock them back and forth, squeeze them together, make a tighter connection, check all your hardware. Pattern switching is a perpetual problem in many arrays. Solenoids and microswitches, these are moving parts, and they tend to become intermittent or fail outright. These microswitches in particular. Keep some spares on hand. Kintronics, I'll tell you this, Kintronics contactors, RF contactors, they use 4 microswitches that look identical, and electrically they are, but they are riveted to a little bracket, and each one has a number stamped on it, 1, 2, 3, or 4. You replace a 1 with a 1, and a 2 with a 2, and a 3 with a 3, and a 4 with a 4. So keep at least one full set on hand so you have it when you need it, So anyway, there you go. Porcelain insulators are prone to crack or break. You get temperature swings that can cause the chassis or the ATU cabinet to oil can, and it'll cause those to break. Wind can do it. Seismic activity, it's a constant thing for us in California. We get these little shakes all the time, and they break insulators, Keep a stock of spares on hand and inspect these things and replace them as you go. Boy, that is a brand new antenna tuning unit. Isn't that beautiful? Brand new. That's one of the ones out there at KBRT in Los Angeles. That picture was taken earlier this year, like in February. So that thing went on the air in February of 2013. So that's 13 years. That's been in service 13 years, and look at it. That's the way a 13-year-old antenna tuning unit ought to look. It ought to look like it's brand new, you know? You just got to take care of them. My hat's off to those guys out there. They really do a great job of taking care of that place. Here's a couple of things to look at. There's on the left there. That was at the same site. The picture was taken with the same time that other one was. They were doing their annual inspection, and they found broken ceramic right there. They actually found several, but that was one of them. That was on a ball gap insulator inside the ATU. And thankfully, that piece of tubing that's holding it at the top was rigid enough that it didn't let the ball over to the other one. The coil is something that you should look at and recognize. What do you guys see on that? You notice where it is, where the heat is? Yeah, it's right at the coil clip and above. So it centers right on that. So, I mean, it's fairly obvious what's going on there. And it was all working fine. This was not a problem that had manifested itself yet, but they caught it. And I'll just tell you, Tarnex is your friend. So get some Tarnex, use it, clean that stuff up, tighten those connections up. You see something like this, deal with it before it becomes a problem. I don't know if you can see it or not, but on that phenolic coil form there, that's starting to discolor. And, you let that go very long, it'll catch on fire, and then you really have a problem. Pay attention to your grounding. Look for signs of tampering, theft of the ground system. You shouldn't be able to see radial disturbances in the ground unless it's a brand new array. You shouldn't be able.
This was not a brand new array.
This was not. Amanda went out to this site. Oh, it was. And she went out to the 810 site and, where are all those lines in the dirt? You guys saw this on Channel 9. You just didn't know it. Yeah. Some guy had gone in there, went up to the tower bases, broke through the fence, pulled up, he could see where all the radials were attached to the ring. He cut them, pulled several up at a time, wrapped them around a trailer hitch ball, and just drove. And just pulled those radials right out of the ground. And just did that over and over again and got all this copper out of the ground. We had to spend $30,000 and put a new ground system in. And then I paved over the ground system in the tower base. So we have like a 50 by 50 section of 3 inches of blacktop. And there's no place where you can grab a handful of radials anymore. And we haven't had any more issues. But this particular guy, right up the road at Fort Lupton, was this electrical supply, not electrical supply guy, it was an electrician, electrical contractor. He had his yard there, and in this yard is a fenced, enclosure, and he had a bunch of spools of big wire and all kinds of stuff, and he'd been getting ripped off over and over again, and he put a game camera up there, and he caught the guy. Next thing you know, he caught this guy's image. They put it up on Channel 9. They showed the guy's image, and would you believe it? The guy turned himself in. Yeah, he knew he was dead, and he turned himself in, and he was the same guy that took our stuff right down the road. So anyway, if you can see that, and it's not a brand new array, you got a problem, and you pretty much know what it is. I'll offer this. Radial ground systems, they don't make good lightning grounds. You're only a few inches into the soil, and you're dealing with real small wire. And, at best, you take a grand mile hit, it's just going to vaporize those radial wires. They'll act like fuses, and, and not only do you not have any lightning protection, but now you don't have any ground system either. So, you need to have an array of ground rods, at least 4 around each tower, and with big heavy gauge wire. It goes up to the ball gap, and you should use an exothermic weld to connect the rods. Anyway, just something to think about there. And my final point here is to keep good records, written records of all maintenance and repair activities. Just keep track of it. Note dial indications on your phaser. Yeah, you know what you're talking about.
I just give this advice to anybody. Do it themselves. Okay, first thing you do, log all the cyclometers, every last one.
Before you start anything. Yeah.
How is that?
Yeah. Yeah, because you can tie yourself in a knot. I mean, even making small adjustments, particularly if you don't know the personality of the array, you can make a mistake pretty early on and get yourself in a knot. And if you've got all those dial readings, you can at least get back to where you started and take a different approach. So something to think about. I didn't put it on here, but the same thing on coils with clips on them. It's a good idea to take a Sharpie and mark it with a color. And then if you end up, having to make a change, mark that with a different color. And then you put it in your record. So you know that we started at the red mark, we ended at the green mark. That capacitor I showed you that was all blown up, I didn't want to spend $2,000 on a new one. I had, that was a .002. I had a 003, a brand new one on the shelf out at KLZ. So he said he had plenty of coil in series. So I said, good. So I sent him that 003 and it worked fine. But he had to move the coil to compensate for it to get the right leg net reactance. And, that's the kind of thing you may have to change a coil. And if you do, having those marks on there, it can save your life. And anyway, and keep track of those seasonal parameter shifts and the required actions. So you know what's what. You know when it's a seasonal shift, you know when it's not. That's it, folks. I'm out of gas. And I take it you're through listening. So any questions? Questions or comments? All right. Yes, sir. John?
Story about one guy called me up. Patterns are all wrong. Thanks to time to got out there, well, he didn't tell me out there. The phase monitor is not calibrated. Reference power at all. So he had just playing with that. I didn't have really, it was back in the early 80s. So I didn't have, I think I call this guy. Haven't come out. I don't know if I asked him if he wrote down numbers on the phaser. He did it back to that.
Hopefully somebody wrote them down somewhere. Amanda keeps up. She has a on her tablet.
Well, it's OneDrive.
Yeah, and it's all in OneDrive, and she has a little stylus, and she writes it and it prints it, and she keeps track of all that stuff. And
Try to keep track of all that.
yeah, so that's important. Anyway, buy one of these if you don't have one. It's a nano VNA. By the way, that screen where I showed you the spiral Smith chart, that was the program that goes with that. You can do all this stuff on the built-in screen, but you get a lot more resolution on the computer. All right.
Well, thank you guys for coming. For those of you who weren't here when I did announcements, in 1 month, Friday, July 17th, that'll be our annual picnic up at Lookout Mountain. We should be at the same spot at the picnic area, at the park. obviously, if they decide to do another
Gonna keep it?
emergency training and tell me last minute, I'll do my best to let you guys know. But please sign up for that. We have until July 3rd to sign up for that because I have to give a number to Famous Dave's. So, but hope to see you guys
It
then.
was less than 290. And it comes with cables and calibration loads. Yeah, so I mean, here's what it comes with.
Bye, Rich.
Calibration loads.
Thanks for joining us.